all time. But I can guarantee if any of you have tried to write in this way, it is very challenging. It really forces you to think through, what am I trying to say? How can I say it clearly? And how can I use language that is the most clear? I'll also say that it's important to actually test your materials with your audience. So what I'm showing there on the right is a graphic that I thought would be pretty straightforward to develop to explain the biobank to men in the prostate cancer cohort that I talked about in the beginning. It actually took 4 what we were trying to say with a biobank. So this had substantial audience or cohort participation in the development. And I think without testing with the audience, you often don't know whether you're clearly communicating or people even understand what you're describe. It's very hard for people to understand future uses for biospecimens where you don't actually know what you're going to do with it at the time they consent. And then finally, really starting to think seriously about alternative formats. And I know some of the All of Us sites have started to think through this. But when you are working with people who have limited health literacy, they tend not to seek information through print. They tend to rely more strongly on interpersonal sources as well as audiovisual and other ways of information. So I've had great success personally working with what are called lay health advisors or community health workers, people who are trained to go out and recruit in their community or work with their community and act as a liaison between a particular that I'm showing there at the bottom is from a video developed by our own Genetic Science Learning Center here at the University of Utah, who has really started to think about audiovisual ways of conveying this type of information. And then I personally have started exploring the world of chatbots and avatars, but tools that can be embedded within the electronic medical record or health record and help people walk through a recruitment or informed consent. So just to finish, I think there is a broad need for research in this area. I think one of the issues Jim raised is we don't actually know what people want to know when they think about the All of Us cohort. We are making assumptions as researchers about what people want to know. And I know there are some great efforts available or ongoing to figure this out, but we need to have a better sense. Do people want to know the terms DNA, about the importance or not of targeting strategies by population subgroups? You can see that there are some common issues across the population subgroups, and then there are some differences. And so to what extent can we use the same recruitment strategy for all populations, or do we really need to start thinking more seriously about targeting? And then finally, research on the effectiveness of different communication formats, so weaning ourselves off of our reliance on print and getting more serious.
It's also a pleasure being here. The only time I've ever been to Salt Lake City is through your airport and connections. So this has been my best visit yet, I can promise you. I wanted to take my talk a little bit further. I'm very interested in how we take scientific knowledge and actually make decisions in clinical contexts about that. So I'm going to sort of focus on what I call crossing the finish line. So I'm going to talk briefly about why precision medicine is so hard in this respect. It's a very difficult domain of science to take and put it into the clinic. And then I'm going to close, if I have time, and talk a little bit about evidence-based medicine and what lessons we might learn from that field to inform precision medicine. So really the main question that I want to answer here is, how would healthcare providers tailor treatment to particular subpopulations, okay? sounds like a relatively easy question. It's actually quite complex. So let's just think for a second about what precision medicine is, how it works. There's sort of big data analysis, and there are a number of different folks in this field call insights, okay? And then the task is taking what we call insights and making that part of clinical care. So how does that happen? So to answer that question, I need to tell a little story. So and ultimately one of the sort of conceptual founders of computing in a time when computers weren't really readily available or existent. He played a major role in that. So many of you may have seen a movie about a portion of his life where he worked in Project Ultra, which was part of the UK military, and they military, and they were able, their task was to take messages transmitted and encrypted by the Germans and to decrypt them so that they could provide intelligence to the UK military. Several of these Enigma machines available to them, they could open them up and see how they worked. It was a key piece of the task. So essentially their goal was to take, they knew that the getting some kind of output, which was an encrypted message. So their goal was to take this black line, go back to the beginning and tell the military what that original message contained, right? Is essentially decryption. Today, this is, bread and butter. We have all been using it during the talks, right? But at this time, it was a very big challenge and no one knew how to do it. And as I said, the great thing and the thing that actually made it possible for Alan Turing to be able to achieve this is that they actually had Enigma machines sitting in their laboratory. They were able to literally open the box up, look inside, and figure out what was going on there, and then they were able to develop a very rudimentary computer to run the encryption backwards. So they were able to decrypt these messages. Okay, so that's a major piece of precision medicine today. We have this box, right? It takes things from the outside, it goes through this box, and it puts outputs, right? Phenotypes, we call them. So the question that we want to answer is, we want to run that backwards so we can take the output and figure out what we need to put in order to get healthy, right? So what do we have to go back and put in, whether it's medications, environmental conditions, what do we have to do to make this box work better, right? So all of biomedical science up to today has been trying to figure out what's going on inside this box, right? We want to open up this Enigma machine, look inside, and say, what's going on here? What are the mechanisms that cause this input to lead to this output? Once we understand the mechanisms, we can then take advantage of that to create pharmaceuticals, to do whatever in order to make people healthier, right? Okay, so that was early part of Alan Turing's career. Later in his career, he became interested in a slightly different model of computing. And he proposed this idea that's now called the Turing Test. The Turing Test, he basically, it's kind of a thought experiment. What would it look like if we were able to invent some sort of tool that could simulate human interaction to the extent that a human couldn't tell they weren't interacting with a human, okay? So the idea here is, how does conversation come about in our own lives? Well, we have this box. We don't really know what goes on in there, but for some reason I come out with an output, okay? And I say something in response, okay? The key part here is we actually don't know what goes on inside this box, right? It's complex. We've spent 3,000 years of human scholarship trying to figure out what goes on inside this box. We still don't understand it. And so Alan Turing's challenge was, well, without understanding this thing, could we come up with a model that's capable of simulating what goes on so well that you couldn't even tell it's not the same thing, okay? So if you think about it this way, early Turing was working on simulation based on mechanistic understanding. We're trying to simulate this Enigma machine because we understand the mechanisms. The late Turing, his work was saying, let's develop simulations that are intended to simulate without a mechanistic understanding. This is also a major dimension of precision medicine. We label it all under kind of precision medicine, but it's actually two very different things, and I'll have to admit it's a spectrum, but both of these things are going on. So think about understanding. It's the science we've been doing for several hundred years, except for now we're just doing it with a lot more precision. The late Turing dimension of precision medicine is that we're developing insights that don't depend on mechanistic understanding. So I'm just driving this message home. Precision understanding of the mechanisms of the human body, machine learning algorithms that predict response to treatment, so they do not reflect mechanistic understanding. Okay, so here's the question. I said all of that to ask this question. Can a black box, i.e. non-mechanistic precision medicine insights, be used in medicine? Okay, this is a $1 million question right now. Everyone wants to answer it, right? Okay, so let's talk about existing applications of machine learning. Google has absolutely mastered this, right? So you enter your search terms over and over and over again. Other people enter their search terms, then they get a list and they pick one of those things. And every time someone does that, Google gets better at predicting which one you're going to click, right? It moves it up to the top. So this is, they use machine learning. There's a lot more going on here than just machine learning. There's lots of technologies being used. But essentially, this is big data machine learning. Amazon does people who have bought the same things as you end up buying. So these are both extremely effective uses of machine learning that I suspect every single one of you has used. Okay, but remember, this application of machine learning works because Google and Amazon, the tools that they provide, the user already has an idea about what they're looking for. When you type in something into Google, you have a general idea. Involves a choice by a human, okay? Amazon does not take your recommendations. They're recommending you buy this, you might want this. They don't just ship it to you, right? You have to decide whether or not you want that thing. And I'll tell you, sometimes they recommend things to me, I really don't want them in my house, right? So maybe I've bought the wrong things in the past, I don't know. But the key thing here is there has to be a choice, right? If you just let Amazon send you things it thinks you might want, it's going to be wrong sometimes. So there has to be a about making clinical decisions. So in general, clinical decision making in the modern world is about taking patient-specific knowledge and then general, which nowadays we think of as scientific knowledge, putting them together in order to go clinical plan. I left it out of this graph for simplicity's sake, but there's also a negotiation between the patient and the provider to figure out what the best plan is, right? I'm going to leave that out for the purposes of this discussion. Okay, so what actually happens in clinical care is some balance of these two things. On the top is evidence-based medicine. There's patient characteristics, there's comparative effectiveness research. Evidence-based medicine has absolutely mastered the practical decision-making process of how do you go from science to a decision. No one does that better than physiological data and mechanistic understanding. Then there's a mechanistic reasoning process. This goes on a lot in rare disease treatment. It also goes on in ICUs where there's sort of like the numbers on the machines that go up and down. And there's not a lot of evidence behind that, but the providers know, they have enough experience and practical experience to decide, okay, this has gone up, I can do this to make it go back down, right? Whether it's blood pressure, okay? The providers know how to put that together and come out with a clinical plan, and then obviously there's negotiation with the team and with patients. Okay. So the question here is, we know patient-specific knowledge, and then there's maybe a machine learning algorithm that gives us some kind of output about you should do this. But the question is, how do we make that decision? Like on Google, clicking the link that fits what you're looking for. Did Amazon recommend to me the right thing or the wrong thing? Okay? This is a absolutely critical piece of medicine, because if I click the wrong link or I order the wrong thing on Amazon, there's no return policy, right? This is done, and if someone gets hurt, they're hurt. So clinicians and patients need enough information to make a decision about whether to follow a black box recommendation, okay? This kind of precision medicine recommendation. Another way of saying that is, in order for a clinical algorithm to be useful and not dangerous, its rationale needs to be transparent enough to the provider and the patient to make a decision, good idea, bad idea. So I think there are a couple of ways to do this. I don't think this is rocket science. One way is to take non-mechanistic insights, black box types of things, and use them to understand the mechanisms, okay? A lot of the stuff that's going on at BioMarin and other places is exactly this kind of thing. We start with the big data stuff, the machine learning stuff, and then we use that to understand the science. Then we understand the mechanisms, and now we can do care based on understanding those mechanisms. You can also use evidence-based medicine, right? So you have a non-mechanistic insight, you use that to identify what are the therapies, what are the subpopulations that we might want to match up. Now we can do comparative effectiveness research. I wasn't even paying attention. A few minutes. Okay, great. Okay, I have heard this more than once. What used to be called personalized medicine, what's now called precision medicine, that some of these insights are so compelling and important, we should not do clinical trials, okay? We should just put them into practice. The logic here is, the metaphor is skydiving. So we don't do a clinical trial of parachutes, right? Because you don't randomize people to either jump out of a plane without a parachute or jump out of a plane with a parachute. You give them all parachutes, right? Insights are exactly this type of thing. We can't do clinical trials because this stuff is so awesome, it just works, right? I think that's wrong, because it's really about learning are going to be extremely useful. We won't know if they're useful unless we test them in clinical settings. So in just the few minutes that I have left, I wanted to talk a little bit about why it's so hard to do comparative effectiveness trials on precision medicine. So just to remind you, evidence-based medicine is to start with patient characteristics, comparative effectiveness research, shake and bake, then you have a clinical plan, okay? So generally speaking, comparative effectiveness studies are structured this way, that you have a population, you randomize to treatment A or treatment B, you look at the outcomes of treatment A and treatment B, whichever one has the better outcome, that's the winner, right? This is comparative effectiveness. You subdivide the population into smaller groups. So there's definitely the problem just of numbers, right? So you have a smaller number of people who fit into your subgroup. Maybe in this case, it's only 10 subjects. Half of them get the standard of care treatment, half of them get a new therapy, and then you compare the outcomes, right? That means you need to start out with a much larger group, thus another way, some of these subgroups though are extremely rare, and it would be very, very difficult to design a clinical trial that would ever work for such a small subpopulation. So there's the challenge, how do you design a study where the subgroups are really quite small? Well, the most promising way is that you don't split them out. What you do is you design an algorithm, a strategy, and you randomize people to be in the one-size-fits-all therapy. That's the conventional approach. Or you take all the different precision therapies, all the different hypertension medications, you're going to specialize. Each patient gets their own strategy of hypertension group, okay? Seems like a great idea, and it's really the only thing we've got, but it's not perfect. So just think about this. If you, in this group, there are maybe a small subpopulation that actually do pretty well in one-size-fits-all therapy, but we got their targeted therapy wrong. Now the new therapy, even though as a group it looks better, which is what's called an N of 1 trials, which is the same patient starts out with treatment A, then there's a washout, and then they get treatment B, and you see which one worked better, okay? So this is really how a lot of chemotherapy trials are going, that you start with standard chemo, and then you get a precision chemo. The problem with this is that there are carryover effects. The fact that you've gotten treatment A in the past influences the efficacy of treatment B. There's ordering effects. It matters whether treatment A or treatment B goes first. There's irreversibility. There are some things that treatment A creates that will always affect the measures that you're looking at, regardless of what happens with B. On to standard treatment, this is probably our biggest problem, because almost all precision medicine treatments in the realm of cancer are being used as backup therapy, but for all the people who failed the standard therapy. But that doesn't mean that just because it serves the people who failed standard therapy well, that it will serve the whole population well. We don't know that yet. And this is my last slide. So the N of 1 trials, equipoise is a challenge. Is it okay to withhold standard of care in order to test out a precision therapy? Especially in the realm that I'm in pediatrics, ALL in certain subgroups has a survival rate of 95%. So we're going to not do that to try out a precision therapy? It's a hard case, right? There are some other things, in precision therapy where we know and treat those mutations, and they're not the standard therapy. Does it make any sense not to give them standard therapy? This is maybe as one of those situations that we're asking the parachute question, right? Really? We're not going to give them that thing? It sure seems like it's going to work. So there are major challenges here with the ethics of trying these things out. That's all I've got.
Okay, so questions? I don't know if you want to sit or stand. It's
They're not be able to see us if we sit.
okay. Opening up the floor. Yes, go ahead, please. And here we go.
Are we using electronic health record databases to feed into evidence when you talk about individual care versus the larger community?
Yeah, so the question, I think this is actually a major thread of this work. This is called the learning healthcare system, right? That you use the information in the electronic medical record in order to test out whether what you changed is actually working, right? I think it's a great source of evidence. It's going to be very, very important to us. We try something new. Our evidence is that it seemed to work in our medical record. Okay, now let's make that the standard of care. That's probably the wrong approach, right? So there needs to still be a lot of structured evidence-based medicine, comparative effectiveness trials, and there also needs to be, Did our change work? No. Why not? Let's understand the mechanisms. So then we really start to see. So anyway, great source of information, but not the answer, not the final answer.
And we have a question over here, and then
The young lady, one of the problems we have in medicine is knowing when the patient really understands. So we have this very big difference. Emotional reaction to those words and an adequate concept structure of what those words mean. And very often, patients may have heard the words, may have an emotional reaction to them one way or the other, but not have a very clear concept structure. That happens very commonly with statistics.
Yes, it's such a good point, particularly about the familiarity data. It doesn't imply that they have deep understanding or even really conceptual understanding of what those words mean. And I alluded to this really briefly, but they went into, in that particular study, they asked people what they thought the words meant in their own words. And that's where they got the data that people thought of DNA in the criminal justice context. Genes, they had kind of heard of. Angelina Jolie was, the story was getting a lot of coverage at that point, so they associated it with particular celebrities. And so looking at conceptual
Thank you all. Alan Morris. I have a question for Dr. Brothers and then one for the panel. I think there's an alternative model, and that is to recognize that the clinical decision maker actually performs well below our goals. The goal is to make the right decision the first time and every time, and frequently clinical decision makers do that 1 time out of 5, right? You wouldn't fly on a plane if a pilot did that. It's of working memory, short-term memory limitations. Humans can on average manage 4 ± 1 constructs before decisions become degraded. And we for 30 years have been doing that to write rule-based systems that can then be used for comparative effectiveness research. But the difference is we know what's going on inside the protocol. The rules are complete, whereas ordinary comparative effectiveness research is incomplete. We don't know what's going on in the heads of clinicians. And then my question for the panel is, how do we balance the commitment to individual liberty, which is so emphasized in the United States as opposed to the UK, and the responsibility to social needs, which is so much more emphasized in the United Kingdom? The first in the United States and the second in the United Kingdom. We got lots of examples where our information is used for social purposes or business purposes without our permission. And there's an interesting book written about that entitled Who Owns the Future? We give information to Google, they make a profit, we don't get paid, as an example. So I'd like to hear your comments. With independent liberty, and you might have some comments about this alternative model for which we have a lot of experience locally.
Yeah, I'll answer that, and then I'll let these folks answer the second question. Your point is well taken, and you see this reported quite a bit that there are machine learning strategies that outperform clinicians, right? So I don't deny that there could be a lot there, right? That when it comes to very focused tasks like identifying whether a mole is melanoma or not, that machine learning could outperform a clinician, and we already probably have the technology to do such things. We should use those technologies. But remember, I don't think I'm telling you anything you don't know. The process or the task of making a decision in a real clinical context is much more than whether or not that mole is melanoma, right? there's a whole set of interpreting the patient's value. Whether this patient matches the sample on which the data was trained, or in evidence-based medicine, we would say the cohort in which this comparative effectiveness research occurred. So there's there are many, many questions that need to be kind of individualized at that final step. And I think, and finally, there's also just the core problem of responsibility. So is a machine making that decision, or are human beings making the decision?
I'm not talking about machine learning. I'm talking about production rule systems generated through knowledge engineering. So the clinicians are actually making the decision, but it's done asynchronously. So the rules are captured before the actual patient encounter. That's a different model from what you described.
It is. And I completely agree. We ought to keep moving that research forward. I think it's quite going to be, it already is important, and it's going to be far more.
Important thinking about the balance between individual liberty and social good. I'm a communication person, so I think about communication strategies. I think the best evidence we have is that being transparent about what we're doing actually helps to achieve that balance to some extent. Not for all patients, but I think certainly in the work of people working on biobanks, biorepositories, data sharing, where you get yourself into trouble is if, and I'm thinking about Jim's example of all of us, if people don't know what you're doing and then they find out later that you've shared their data or you've used their biospecimens in other research studies and they didn't know that was going to happen. My own work in biobanks, I found that people broadly are pretty willing to participate in biobanks. They're pretty willing to share data, but they really want to know what's going to happen. They want us to be transparent about it. And I think really thinking through that and taking it seriously, taking our responsibility to be transparent seriously can help with that balance. And
With Peter Pronovost and Tom Beauchamp from the Hastings Center that argues we need a new bioethical foundation in which we're all committed to comparative effectiveness research as the default, rather than going to get informed consent, which is our current approach. Our current approach is opting in, and they argue that we ought to all be opting out when there's a legitimate.
yes.
I think you've stumped the panel on that one. Here, let's get a question over here.
This is for our first speaker. I enjoyed your critique of the All of Us cohort study that's currently starting up. I would suspect from what you said that you would recommend to friends, acquaintances, colleagues, and in your writings that everyone should decline to participate. So I'm questioning, my question is, what do you actually say to friends, colleagues, associates, and what do you do in your writings about whether people should enroll?
I'm working on a book on the history of what built up to, from the Human Genome Project to the All of Us program, sort of where this idea came from, what were other ideas that could have happened and didn't. So I enrolled purely in the name of research, but not that research, historical research. You know, if you've got resources, then precision medicine probably will help you. Being able to benefit from precision medicine is going to hinge a lot on whether or not you've got resources to benefit from precision medicine. Access to healthcare, access to if you want to join this program that's going to make that more widely available, knock yourself out. If that's not your interest, if that's not what you think medicine should look like, then I would encourage you to think.
My question's for the panel. As a med student, we've been learning about EBM and the importance to make subgroups and stratify our patients. How do we know if we've done enough or if we've gone too far and over-stratified our patients, and what would that look like?
That's the million-dollar question. I mean, and perhaps even a harder question is, precision medicine used to be called personalized medicine, right? We don't do that anymore because it's hard. Also conceptually very, very challenging, right? Each individual person having their own thing, that's not science. It's so hard to imagine, like, what would we need to make science like in order to make that possible? I would say, I don't know the answer to your question, but we'll say individual level stratification is over stratification. It's just not possible. So I really like the name precision medicine because I think it's a lot more accurate. And then, you know, even if there is a treatment that is the most effective for a particular subpopulation, there are those individual things that are not scientific in nature, that are more social, cultural, and economic in nature, that may make it not the best treatment. I mean, yeah, I don't know the answer to your question, but one's too small. Yeah.
Okay, I think over here.
Oh,
Sorry,
I had
right.
one. Yeah, thanks.
Dr. Carter.
We're bouncing around as you always do in these type of panels. I'm coming back to Jim on the all of us thing. Advisory panel, that doesn't mean they listen to me. But I would say in this day and age, it is absolutely important to get facts right. And some of yours were not. So NHGRI didn't design that study, and the working groups definitely had environment, and so that could be debated. But it doesn't. It doesn't matter, because your point is right, that genetics doesn't come out on that. And everybody that's associated with all of us have recognized this. Now, I think what Francis and co would say is that's an active, I'm not speaking for them. And it really is meant to be, in all the meetings we have, the discussions are much more about the environmental measures and childhood and tribal relations and these type of things. And that they're actively trying to minimize the genetics by design of the study. So my question to you is, what if the situation weren't the malicious case that you kind of described, that everything's being hidden by the geneticist, but actually they were trying to do the right thing and put genetics as one piece of the puzzle? Does that change your position as an opponent or?
The way you might describe the second model was aspirational, right? And I don't think there's a clear line between it being malicious and aspirational. I never said anybody lied. I don't think there was intentional deception here. I do think it was the case. I mean, they did design this thing with the vision. I mean, all the design components that went into it, the sample size, the convenience sample, how the resources are distributed for where the data is going to be coming from. Now, you could say, yeah, but they're going to get some environmental stuff too. And I agree with that, right? It was never like it was only going to be genetics or it was only going to be environment. But, you know, the question is, you know, the way I described it was, genetics was in the driver's seat and the environmental stuff is just coming along for the ride. And, you know, the thought is, if you would have given the same amount of money to a bunch of social behavioral environmental scientists and said, go design a national study that you think is going to, you know, maximize health in the United States, this is not what they would have designed. Now, I agree facts. What I meant by it was designed in the Genome Institute is when you go back to the origin, the end of the Human Genome Project, immediately what they create over there is something called AGES, the American Genes and Environment Study. It was a massive genetic study with environment along for the ride. It was what all of us was going to become. It was a massive genetic study where they were going to get genetic information and then they were going to get some environmental information via smartphones and surveys. That's the sense in which this is, you're right, it was moved out of genome physically. Not just geneticists were part of the design, but when you just look at the history of how this thing unfolded, there is no clean break.
Okay, great. So we've got a queue here. And if we have time, we have just 10 minutes, so let's, so go ahead.
Thank you. My question is really very social and ethical, and I'm curious as I'm listening to everything that's being presented, and I applaud all of the work that's happening. Specific communities or cohorts, there's a lot of information that these communities have already about their conditions, genetic conditions specifically, that do not present until, let's say, after contact with very specific pharmaceuticals that they later find out after being diagnosed, because their disease presented after a pharmaceutical that was actually contraindicated for a primary diagnosis, that to that point their lives had been missed. And this is a very common experience in the rare disease community. And I'm curious if anybody is attempting to engage the communities, the patients specifically, to take histories like that, or to ask questions. Precision medicine, and I understand the desire to want to, first of all, identify, because we need to find the conditions, and then we need to treat them. But as somebody who's working closely in these communities, I see a lot of patients who have very common experiences where harm was done that could have been prevented had they known what they had.
I don't know if any of you guys have anything to say about that, but I think we are long past the community of scholars opening up the doors to such people. What actually happens is those people said, lots of great efforts that have been led by disease advocacy groups who go and find investigators to study their samples, who collect their own samples and then, you know, go and hunt down people who will do the kinds of things that they want them to do. Et cetera, as you know. So, yeah, I think, you know, that group of people have done amazing work, and they led the way, and we followed. And I think that has opened up the eye. I mean, all of us, at least in its aspirations, wants to really open the doors to those people and let them play a major role in making decisions. So, yeah, it is a big question. There's a lot that still needs to be done. But we've been following their lead for the last decade, I think.
Okay. Well, we've got in the queue, gentleman in the middle, and then Dr. Yandel, then we'll come back.
So in the world at large, there is a institutions, which includes mainstream biomedicine. You see this most strongly in politics. Vax movement, et cetera, et cetera. So my question is, if the message here, or the hope here, is that we get larger and larger cohorts of high quality data and everyone participating in this, how can you do that if these cohorts are organized by institutions that are seen as large faceless institutions?
Yeah, it's such an important question. The prostate cancer cohort data that I mentioned, where people agreed to have their biospecimens used in future mistrust of the specific hospital where that data were collected, were historical reasons for that, both frankly among white men and black men, high levels of mistrust. And so one of the things we've been working on is communication strategies, trying to overcome the mistrust, but it's only helped in reflecting on the last question also is the extent to which this is a partnership with a particular patient community or disease community. So it's not necessarily seen only as a federal government venture, but it is an extraordinarily hard problem to overcome. And particularly as we ask and Jim.
Okay, so we've got a queue going. So Mark Yandel is next, and then gentleman in the back, and then okay, go ahead.
All of us, design study. I'm a little confused here. If the goal is to tie sequence variation to social and economic outcomes, I mean, you're going
I agree. And that goes back to the point about when you're making these design decisions, there's no sort of in a vacuum right answer. It's going to depend on what you're interested in. So if you're interested in rare diseases, then and rare diseases that seem to be associated with something genetic, common diseases that affect people up and down the socioeconomic genetic, but it might be something in the environment, but it's not as obvious as just drunk driving, then getting lots of information about their environment, could be their home environment, could be their neighborhood environment, could be their school environment, could be their personal relationships with their employees, that's gonna be relevant, and how it plays out in different socioeconomic groups is gonna be relevant. But now that's a different interest. You've got to decide, we want to understand that, do something about that. Different from saying, we want to understand rare diseases and do something about that. You didn't say anything that I disagree with. It's just the point is that's a decision. It's not that you've got the right answer and this other answer is wrong. It's you're prioritizing something and they were prioritizing something else.
I gotta say one last thing. In that rebuttal, I'd just like to point out there's all of this binary logic, this, not that, yes, no, 1, 0. And the whole thing with all of these new technologies, and it's not about this kind of binary mode of thinking or even these binary ways to probe the data. And so what you can and can't get out of a study is often very subtle and not even really immediately obvious from thinking about things in these sort of yes-no sorts of ways. And I think that's really the big change that's undergoing as we probe these big data sets.
Okay. So gentleman in the back's been waiting very patiently, and then we'll go back here, and then that'll be it. So sir, go ahead.
So in relation to your comment about personalized healthcare, application. So I'm a medical informaticist at Intermountain Healthcare, and we have been doing personalized healthcare, but it's not using genomic data. You know, the data driving it is claims, clinical data, social economic data, environmental data, criminal records, credit histories. So the use of genomic data can be more precise, like in the case of pharmacogenomics. We'll run the tests for dosing blood thinners, dosing antidepressants, looking for drug-drug interactions for polypharmacy. Coming closer into today, where do you guys see the merge with the genomic data? Rather than this study, and as you're pointing to rare disease and things, we get so focused on what the genomic data alone can predict versus what the genomic data combine with this vast richness of data. Just your perspective on that combination versus the solo use of genomic data.
Anything particularly controversial that makes sense to me. Getting that data takes effort and takes time, and you've got to decide that it's a prioritization that you want to get. And so you've got to sort of say, we need that because we think that's relevant to the health of our patient population, and that takes work. Sort of just to repeat a point earlier, you could have done something else. You could have got a lot of genetic information. You might want to get that too and add it to it. But right, we don't have endless amount of resources. So there are binary points where you have to say, are we going to do 1 million people or 100,000? That's you're going to get probabilistic answers in response, but you got to make decisions. Are we going to invest the money in getting this data? Trying to get it from both makes sense, right? But it's one thing to say that in theory. It's another thing to sort of actually go out and say, okay, we got to get that because we think that's important. And it's going to cost this amount, and that means we're not going to be able to get these other things.
And I'll just have one more response to that. I'm not a statistician, so I hesitate to wade into this territory, but I've worked with statisticians, and I know that as I start adding more variables to my model, the sample size that I require in order to there are questions that in order to answer them, the sample size would literally have to be more than 8 billion people. And 8 billion people exceeds the current population of the United States. So or not the United States, the world. So there is a problem that we are going to have to face, that more data is awesome, and we can develop models that incorporate lots and lots of data, but we still have the problem that there are counterfactual events of people who exist outside the human population who have combinations of things we've never seen before, and we don't know what those sets of combinations are going to lead to. So there just has to be still a little bit of humility that, yes, answer.
Yeah, I'd like to follow up that question. Alan Morris again. First of all, if you look at Bell's number, the number of ways a complex system can be partitioned and study all the interactions, even for less than the most complex patients in clinical medicine, it would take us Koch estimates in a Science article. I absolutely agree with you. We're not going to get to where we want to be to have an appropriate level of evidence for most. Point out that I think Jim Tabery is onto something very key when he says we have to think of what we're trying to achieve. And that gets to a term that's used by psychologists and sociologists called choice architects. We're all choice. They enabled certain things to happen in this room that couldn't happen where we had these conferences when they first began, because the architecture is different. But clinicians are also choice architects, and surveyed have a lot to do with how you anchor people, and that determines what their response is. If we all went to buy a car, we'd probably find a salesman first saying, well, you know, it's about $35,000, when he's willing to sell it for $30,000. If he started off telling you it was $25,000 and then said, well, I actually have to sell it for $30,000, you'd walk out of the room. But by anchoring to $35,000, so the idea of defining, insofar as it's possible, what your goal is, I think is a much more important issue than just, well, one of the possible things we could do. And I think Jim is on to.
Thank you.
Okay. And I think we really have just time for one last question. We're a bit over, but please go ahead. And then,
okay, thank you. This is a question for Kyle Brothers. I really enjoyed, I liked your framework for decision-making. I wondered about incorporating the decision-making around diagnostic testing, diagnostic evaluation. And we have to, we do better not proceeding further with additional diagnostic tests. And can you speak to that, these kinds of issues around diagnostic decision-making?
Yeah, that's a really great point, and I, in a number of ways, oversimplified my model in order for the circumstances. But really, there's multiple decisions, right? And so there's decisions. So yes, this is absolutely, as everyone who's been to a doctor knows, this interaction is an iterative interaction. There's the choice about getting more information, not getting more information, what we do if we get certain things, you know. I'll just close by, the first lesson every medical student learns is you never order a test, you don't know what you're going to do with the result, right? And so that is a humongous problem, and just the whole idea of clinical and sets it on its head and asks, what do we do? So I think there is period. Yeah.
Okay. Did you, one more short, very short, no?
It was just a comment about what you say about large data. It's not about how big is it. I mean, it's not about how big data doesn't necessarily is better. It's necessary, but it's not sufficient. What is critical topology of that region with enough density to make predictions. So if I measure the altitude in the whole valley of Salt Lake, I learn nothing about the mountains.
Right.
So your sample technology is what really matters.
Fair enough. Let's thank our panelists. So we do have lunch back here for everybody, and we'll resume promptly at 1:30 with the next panel. So thank you very much.